Okay, so in this video, we're going to talk about the graph of the tangent function. So y equals the tangent of x. Now, we're going to define this. We're going to graph it on the interval from negative pi over 2 to pi over 2. This interval, the period for the tangent function, is equal to pi, if you'll recall from an earlier video. You think about tangent theta, or tangent x, is sine x over cosine x, right? So as long as cosine x is not equal to 0, we're good to go. Well, what do we know? If you think about a unit circle, where is cosine equal to 0? That's the x value. It's equal to 0 at pi over 2. But also, like if you rotate all the way around, that's 3 pi over 2. But if you rotate this direction, that's negative pi over 2. Okay, so we're only looking at values on this interval here, and then you can just copy and paste if you did want to graph it. So just like we did in the other videos, let's make a table of values. So I have tangent of x. So let's just pick some random values. So negative pi over 3, negative pi over 4, negative pi over 6, 0, pi over 6, pi over 4, and pi over 3. Okay? So with these values, all right, if I plug in, I'm going to have 0 at 0. Okay. So first point right there, that's 0 and 0. Tangent of pi over 6, well, let's think about that point right there. That's square root 3 over 2 comma 1/2. So that's 1 over the square root of 3. Okay, which is equal to square root 3 over 3. All right, so pi over 6. So we're up to this point right here. Pi over 4. Let's see, pi over 4, that's 1 over square root 2 comma 1 over square root 2. So if I divide those, I can just get 1. Okay, so now if this helps you, square root 3 over 3 is like 0.58. This is 1. So we're just moving on up. Okay, and then let's see here. Pi over 3, if I do this here, that's 1/2, and then square root 3 over 2. If I divide those, I get the square root of 3, which is like 1.7 something, I think, 1.73. Okay, so maybe something like this. So at pi over 3. Now at pi over 2, if I tried to evaluate at pi over 2, it would be undefined. I'd be dividing by 0, so you can't do that. So what's happening? I'm getting really, really close. I can get really close to pi over 2, but there's a vertical asymptote right there. Okay? Now if I run this other way, tangent is an odd function, and so this is going to be negative square root 3 over 3, which is like roughly negative 0.58. This is negative 1. Okay, so the same game is getting played here too. So negative pi over 6, negative pi over 4, negative pi over 3. The closer I get to negative pi over 2, the further down to negative infinity I'm going, and vice versa up here it's going up to positive infinity. Okay, so this is what the tangent graph looks like. So if you were to graph this, okay, maybe it would look something like this. Okay, vertical asymptotes at odd multiples of pi over 2. Okay? So that's what the y equals tangent x graph will look like. All right? So what do we have for the tangent? We have vertical asymptotes. X equals, let's see here. Two k plus 1 times pi over 2 for k as an integer. Vertical asymptotes. Okay, so those are vertical asymptotes right here. Okay, so just summarizing everything about this here. What else? What other properties do I have? The domain. The domain is all the x numbers except for odd multiples. So all x values except for odd multiples of pi over 2. Now, if you were asked to put this into set notation, what this would look like, it would be x such that x is not equal to 2 pi or 2k plus 1 times pi over 2 for k an integer. Okay, so if maybe you have a more advanced class and they ask you to put it in set notation. Now an integer in set notation is represented by z. Okay, so if you want to use that, that's fine. I don't care, but at least at the minimum, write it out in words, all x values except for odd multiples of pi over 2, because that's where the vertical asymptotes are at. Now the range for the tangent function, this is going from what? Negative infinity all the way up to positive infinity. So the range is all real numbers, negative infinity to positive infinity. Another way to write all real numbers is the set notation R here. Okay. So the tangent function is odd. So that means it's symmetric with respect to the origin. So what does that tell me? That tells me, tells me that the tangent of negative x equals negative tangent of x. So that property might be useful. The period, okay, we talked about this, but the period, since we're summarizing, the period here is pi. Okay, so the standard period is pi. The intercepts, where do we cross the x-axis? Do we cross the x-axis? Yeah, we cross the x-axis infinitely many times. So the x-intercepts are what? They are multiples of pi. Okay, so k pi, where k is an integer. All right. So that's like negative 2 pi, negative pi, 0, pi, 2 pi, and so on and so forth. Okay? So the y-intercept, is there a y-intercept? Yeah, it looks like there's one y-intercept at y equal to 0. Y-intercept, we have y-intercept 0, 0 here. Okay. All right. So I think that pretty much gets your tangent going there. Let's do an example. Okay. What if I had a graph of a tangent and it was like y equals a tan omega x, okay, plus some b here. All right, for tangent functions, there is no concept of amplitude, since the range is going from negative infinity to positive infinity. It's not bounded like the sine and the cosine. So the role of a in this one is to provide the magnitude of the vertical stretch. Okay, so if you think about it, if your a in absolute value is greater than 1, then we're doing a vertical stretch. And if your a in absolute value is between 0 and 1, then it's a vertical compress. Okay, remember back to college algebra for that. Now, the period for the tangent is pi, okay? So the period for this would be a period of pi divided by omega, okay? This is caused by the horizontal compression of the graph by a factor of 1 over omega. So the b, the last thing, the b, this is your vertical shift. So you either knock the graph up, you knock the graph down. It's positive, you go up. If it's a negative, you go down. Okay? So a, isn't really your amplitude. It's more of, the magnitude of the vertical stretch. Okay? Your period, the only thing difference, instead of a 2 pi period like with sine and cosine, it's only pi. And this is true also for the cotangent as well. Okay, so this also works for y equals a cotangent omega x plus b. Okay, same thing. Period is pi over omega. Okay? All right, so let's do an example, and maybe it'll help out with this. So I want to graph y equals 2 tangent of x minus 1. So use the graph to determine the domain and the range of the function. Let's think about this for just a second. So the domain here, so what x's work, which ones don't? Okay, so the domain, all x's work except for whenever I have a vertical asymptote, and that's where cosine, remember, tangent is sine x over cosine x, right? So as long as cosine x isn't equal to 0, we're good. But it is equal to 0 for values of pi over 2, multiples of pi over 2. Okay? So if k is an odd integer, right? So that means like 2k plus 1 and then pi over 2, okay? For k an integer, right? So things, as long as we don't have things like pi over 2, 3 pi over 2, 5 pi over 2, and then the negatives of those, then we're good to go. We got to avoid those, right? The range, negative infinity to positive infinity. So we're good on that. So if I graph, so let's just run through the graph. Okay. All right. So from negative pi over 2 to pi over 2. And so I know I'm going to have vertical asymptotes here. All right. So let's graph this thing. Let's make a couple of copies here. Uh-oh. Can I make this any smaller? Yeah, that doesn't look too bad. Okay. So let's see if we can graph what's going on here. So if this is y equals the tangent of x, then we know tangent is going to behave like this here. Okay, so y equals tangent of x. Now, at pi over 4, we have 1. At negative pi over 4, we have a negative 1 here. Okay? What are we trying to graph? We're trying to graph this thing right here. So next I'm going to do 2 times tangent. So this is y equals 2 times tangent x. So 0 is still at 0. But whenever I plug in pi over 4, I'm not going to get 1 anymore. I'm going to get 2. It's going to be double. And so it's shooting up even faster. Okay? And then same thing here. I'm not going to get 1, negative 1. I'm actually going to get negative 2. So it's going down even quicker down this way. Okay? With the graph here, this last part, y equals 2 tangent x, and then what am I going to do? I'm going to shift it down 1. It's literally going to be the same graph that I had here in my second one, except I'm going to shift it down. So I'm going to shift it down so where instead of it's at 0, 0, this point here is at 0, negative 1, okay? And so when I come up, it's going to be like this, and then whenever I go down, it's going to be down here. So this one's like, golly, that's like negative pi over 4 comma negative 3. And then this one up here is like pi over 4 comma 1. Okay? So that's what's going on there. Okay? Now technically, you know, this thing is repeating, and so you've got your copies that run through. Okay, so you can draw that as many times as you desire, but you know, if you get the one period, then that's, you know, that's good enough for me, unless it asks you to do more. Okay. All right. You just copy and do your little copy and paste button, right? All right. So hopefully that helps you with graphing your tangent for that. Let's try one more tangent problem. Make sure we're good to go. So I want to graph y equals 3 tangent 2x. So if I graph this, well, what's different here? The actual period has changed, okay? So remember, your period for tangent is pi, but to find it, it's pi over omega, and my omega here is 2. So my new period is pi over 2. It's the new period. Okay? I didn't shift it left or right, but I do have this vertical stretch, okay? So vertical stretch by a factor of 3, All right, so my graph here, all right, so with this graph, you get your pi over 2, okay, so pi over 2 thing going on here. Oh. And negative pi over 2, and so your graph kind of looks like this for tangent x, but we're going to take it and we're going to multiply by 3, so 3 tangent x. What that's going to do is stretch it vertically, so instead of being at 1 and negative 1, it's going to be at 3 and negative 3. Okay. Both are going through the origin. But then, what did we do? Our period is no longer a length of pi, right? The period has been shrunk. It's been cut in half, okay? So by a factor of 1/2. And so now, instead of going between negative pi over 2 to pi over 2, which is a full pi period, it's half of that. So the new period, instead of being dividing by 2, it's actually going to be dividing by 4 here, okay? So this is your pi over 2 mark, and that's your pi over 2 mark. But we're not even going to get out there. We're shrinking it to half of that. So now our vertical asymptotes occur much sooner, okay? Now if they occur much sooner, look, halfway between, so this is negative pi over 4, and this is positive pi over 4. Now here is pi over 8, so that's negative pi over 8, and that's positive pi over 8. So down here I've got my 3 value, and then up here I've got, so down there was the negative 3, and up here's the positive 3, and it's going like this. Okay, so really we're taking a graph, okay, and you can see here it's condensing the period's getting over with twice as fast, right? You can see that, and then it's also steeper on top of that. So kind of a lot going on there, okay? So, but this is 3, so this would be the graph of y equals 3 times the tangent of 2x, okay? 2x. So the period here is pi over 2 because of the period shrinking by a factor of 1/2. And so my asymptotes, you notice that asymptotes now, vertical asymptotes are like pi over 4, okay? Multiples, odd multiples of pi over 4. So like that'd be like 2k plus 1 pi over 4, okay? All right, cool. Now we're going to do the graph of the cotangent.